All right. Hello, everybody, and welcome to session number 2 of our LinkedIn Live workshop series here. Today, we're going to be talking about how we treat our data center and shifting our mindset away from the monolithic thought process that we have traditionally had and into more of a microservices thought process, similar to what we can learn from developers who have taken monolithic code bases and turned them into manageable microservice bases. So a little introduction here for those of you who may not have been here for last week's session. My name is Colin Newberry. I am the Director of DevSecOps at Yahara Software. I've been in this field for about 20 years now, professionally, working with organizations of all sizes. Currently, I work primarily in consulting and work with several organizations on their own DevOps programs and cybersecurity. So as I said, this is part 2 of a 5-part series. So today we were talking about modern mindsets. Last week we had our foundations, and next week we'll be working on project management. So before we get into our recap of last week, I do want to put out a little housekeeping note. So last week was my first time doing a LinkedIn Live session, and there are a few assumptions I had that turned out to be slightly less than accurate. So one of those was that there was some kind of chat feedback option here, and I thought people were able to send me questions and things through the session, but it turns out that's not necessarily the case. So if you have any questions, comments, or you need something more explained, please feel free to leave a comment on the event post. So I will monitor the comments on the event and try to respond to those as I'm able to see them. So with that, our recap of last week here is all about foundations. So anything you do, whether it's a construction project, building a new program, modernizing an existing program, nothing works without a strong foundation. And in DevOps specifically, to make this work, there are 4 primary components that we have to have working before we can make any meaningful transformations. The first of that is a well-documented organization. This isn't just a chart with some headshots and titles on it. This needs to have the clear reporting lines that your engineers, analysts, and other team members can expect to follow. You have to have defined responsibilities on here. People need to know who is responsible for what and where those lines are. And that may be between projects, that may be between teams, it may be at different reporting levels. What is the responsibility of your directors versus your managers versus your engineers and your architects? And who in those teams is actually responsible for their careers? One thing engineers struggle with a lot in the DevOps organizations I've consulted with is I don't know where I'm going. I don't know where my career growth trajectory actually is. And if somebody doesn't understand their career trajectory, their motivation to actually do good work is going to be minimized. So having a well-documented organization is foundational step number 1 to any transformation you're going to do with a DevOps program. The second thing you need is a clear decision framework. Right? Last week I spoke a lot about the decision frameworks and where authority comes from and preventing ambiguity. If you don't have clear decision frameworks, you will fall into the same trap that most DevOps organizations, and honestly, most organizations in technology across the board fall into, and that's decision paralysis. No decision is far worse than a bad decision. People make mistakes all the time. They're called learning experiences. And that sounds cliche, but it's true. If people fear making decisions, then they'll sit and they'll wait, and they'll struggle with getting things through the door. And eventually, you'll build a culture where people are so scared to make a decision that might be something that could move your company forward into the future that they will instead start making decisions based on what they think is the easiest thing to get approved. Next, you need a comprehensive style guide. This is another thing that I have seen 0 DevOps organizations that actually have done well. Some will say, well, go out to Terraform, use their style guide. Some will say, yeah, we've got a style guide here. It's 2 pages that says we use Terraform and Ansible, and here's module composition. That's not enough. You need to remove the ability to have ambiguous code development within your organization. We want everybody to fully understand the standards and the requirements that our organizations expect. We need to know all the approved tools that we can use. We need to know what their use cases are, and we need to know what to do if a tool doesn't meet the use case we have. On top of that, having clear standards is going to enable us to do what we're going to talk about later with microservices, which is to create inherent interoperability between our modules. And lastly, your onboarding process. If you don't set individuals up for success, you're setting their team up for failure. You need to make sure that your engineers, when they come into your organization, are fully onboarded and understand how to work within your organization. Otherwise, it doesn't matter how good they were previously, what they were doing at their last job. When they come to your organization, they need to know how to work in your organization. This isn't 1 week sitting with HR getting your insurance paperwork done, making sure you're getting your paychecks. This is a 90-day plan to work through real coding challenges, shadow other engineers, and understand the style guides for your organization. So with all that, once we have that foundation, we can start talking about the actual coding practices that are going to make us more efficient and more effective within DevOps. So let's start out a little bit with what is a microservice. And most people have probably heard the term thrown around. If you've worked with development organizations, you may actually be pretty familiar with it. But to break it down, it's the smallest component that you can logically deploy that can be self-contained. So this is a single function, single feature piece of code that is packaged in a library, written once, maintained once, used many times. These came out of necessity. Development teams and development itself has existed for about 80 years now since the first true modern program was written. And in those 80 years, we've been building monolithic, sprawling code bases. These code bases gradually became completely unmanageable. We get to a point where you cannot throw enough people at a code base to maintain it because the more people you throw at it, the more complexity you're adding to it. When your code base starts to get to millions of lines of code in a single repository, it's not really maintainable anymore. Eventually, you have to break off teams within a single code base. And now you have teams working against each other, in many cases, trying to control drift and merge conflicts from the other teams who are now introducing new code that may cause your code to have a bug. When this gets so large, you can't properly onboard new developers into your organization. They get onboarded into a team within the code base. Knowledge becomes siloed. Every team only knows about their section of the code base. And then we have to hire entirely different teams to keep up with the documentation, because when we have so many interdependencies in a single code base, a minor change in one section can have catastrophic effect across the entire code base. And so now we need to hire people just to keep the documentation up to date so we can understand what the outcomes of making a small change would be. So development teams saw this problem, they experienced the problem, and they solved it. They came out with a concept called microservices. So when they started breaking these monoliths down, they realized that they could take sections of functionality and make smaller repositories out of them. They could take those smaller repositories and wrap them in an API layer. That API layer then provides the inputs and outputs necessary for these different microservices to actually function together as a cohesive system. Anybody here who's worked in these monolithic applications in the past may remember release parties. These were not a fun kind of party. This was the, hey, we're making a minor change on a Friday night, so by the way, everybody's staying until Saturday morning, but don't worry, management's buying pizza, so we'll call it a party. And not as great as they sound. But once we got to microservices, that whole concept disappears. We can now use CI/CD, and we can actually continuously deploy individual microservices independently of each other. There is no such thing as a major release anymore. We aren't putting the entire code base out there at one time. We don't make these monstrous changes and hope for the best. But wait, this sounds fantastic, almost too good to be true. Is it really that great? Well, to be totally honest, in software worlds, not entirely. In software, there is still an aspect of monoliths that has to survive for an application to really be functional. And that's the business logic, right? So the business logic of the application that pulls together all of these microservices and turns them into a cohesive application still needs to exist between the microservices, right? You may have a microservice for your reporting feature. You may have a microservice for importing PDFs into the system. You may have a microservice for creating dashboard components. But something still has to bring this all together in business logic to make it usable for the end user. However, in DevOps, not so much. And the reason is because cloud infrastructures were actually built to be microservices. If you think of what we have in clouds, they are already, by nature, discrete individual pieces of functionality. They already are microservices. We, as organizations, have forced them into being monoliths. We have taken what was given to us as a completely native microservice architecture, and we have forced it to be a monolith because it matched what we had historically learned and historically done prior to DevOps becoming a thing. So let's look a little deeper at a couple of these to give some examples of what I mean. So in AWS, you have your VPC. A VPC is just the components necessary to make the underlying public and private networking happen. It does not know anything about the compute. It doesn't know anything about the load balancing. It doesn't know anything about the storage. It only knows the networks. EC2 only provides the hypervisor, which allows you to deploy the virtual machines that are going to provide compute services inside of your project. It knows nothing about the network. It knows nothing about load balancing or storage. But there are API layers between the two, which provide clear inputs and outputs so that they can consume information from each other and make an environment that works. Load balancer, another great example. You can put a load balancer in front of your VPC. The load balancer isn't part of the VPC. It is a separate microservice that consumes outputs of the VPC and uses it as inputs to itself to provide the load balancing of traffic across networks which are contained wholly within the VPC. Every service that the cloud providers, Azure, AWS, GCP, every service they've created for us is a microservice by default. So then where did we go wrong? What did we do that forced these microservices into a monolithic architecture that has caused us to have increasing budgets, increasing spend, increased maintenance? Well, this. This probably looks very familiar to people on this call who are familiar with infrastructure as code. So in traditional infrastructure as code, we have our environments. We put them into directories for dev, prod, QA, staging, whatever environments we happen to have for our project. And in the same repository, we create a modules directory. And all of the modules that are being consumed by our environments are going to live tightly coupled inside of the same repository. That is the same mistake that was being made by developers as they were growing their monolithic code bases. Everything lived in one repository. Everything was tightly coupled. With this pattern, if you make a change to your ALB module here, you're not fixing anything anywhere else. You aren't going to have the benefits of code reuse. In fact, this creates a lot of problems for us. For instance, every project is going to contain 100% of its code, which means that every project has its own maintenance budget. Every project's code is maintained separately. Every project will have an element of drift to it. No two projects will have identical code bases when you're done. Every time you make a security update to your projects, you're not making one update and pushing it out to 12 projects. You are making 12 slightly different changes across 12 slightly different drifting projects. Every project is going to require end-to-end testing for every release. We can't centralize our testing, even though it's the same EC2 module for every project. EC2 in the cloud didn't change. AWS didn't change their EC2 for every one of your projects. It's still exactly the same, no matter what project you're deploying. We've just forced these into monoliths so that we could manage them in a way that was familiar. So let's look a little bit deeper at one of the biggest problems here, and that is drift, right? So every time we scale in our projects in ISC today, we take an existing project that works and we copy it and we paste it to a new repository. Then we take that copied project and we start making changes. We make it fit the use case that we have for that specific project. This seems to make sense. It seems like the right way to do things. But then you start to get drift from project to project. And now if I go back to project A and make a security update, that isn't going to get copied over to project B. Project B now needs a completely separate budget for that security update because project B has nuanced changes from project A that cannot be captured between the two. Every change we make is going to be a risk. Every time we make a change to these monolithic code bases for our IAC, we risk breaking something in production. Updates across multiple modules don't work across projects. We have to go in, we have to identify what drift happened, and we have to create a whole new change and a whole new mitigation for every single project that we touch. This limits our scalability significantly. Scaling projects means copy and paste a template and then make significant changes. It's not scale, it's code duplication. We're taking 1,000 lines of code from project A and creating 1,000 lines of code in project B, and now we're maintaining 2,000 lines of code. We're not maintaining 1,000 lines of code twice. Every project is going to have its changes, every project is going to have its own code base, and every project is going to have a maintenance budget. And that means for every time we try to scale, we're actually having a net negative gain in our productivity. And so to illustrate that, I got this little guy here, right? This is a penguin, and penguins are the perfect animal to illustrate IT budgets. They really are. They got the little head in the front there for the ideation architecture phase. We spend a little bit of time trying to figure out what it is we actually want. We don't spend enough time there usually. We jump right into ramping into the project. There's a really steep incline. Well, we get involved, we copy and paste that template, and we start developing on it. We get into our main development phase and we start working. We get through, we get something that works in development, we get it going into staging, we get it into production, and then we ramp down, right? And now we get into our maintenance phase, and that maintenance phase never ends. We constantly have to maintain this code base. So at scale, we end up with penguins stacking on penguins. Every project is its own budget. Every project scales linearly in how much it costs us to maintain. Every time we have a set of projects we have to add a new engineer. This is scaling cost faster than we're scaling productivity. So if that's all bad, then what does it look like when you do it right? This here is an actual sample of our code for deploying a very basic, and this is just a startup project that we use for deploying an EC2 based compute infrastructure. This is the main TF file. This is it. 44 lines of code will deploy an entire environment, and it will do it in a standard fashion that works across the board. A couple things I want to point out in here before I move on to the next slide. The source of this, the source for the modules is not coming from Terraform. We aren't writing new modules. This isn't sourcing inside of its own repository. These are pulling sources from wholly contained remote modules. And each one of these, very importantly, has a version number on it. When we take a template and we want to create a new project, all we do is we compose that template into the new project through parameters that are already defined in the remote modules. So what is a remote module? This is when we have all of our modules have been converted to microservices. We put them into their own repositories. Every single module is its own microservice repository. Each module is entirely self-contained in its own single repository. Every module can be tested independently of every other module, and only one module exists per repository. This is where we start to get microservices from in IAC. We take those repositories and we version them. We apply versioning to every single module so that when we have our initial release, all projects can adopt it. If we have a new feature we want to add, for example, maybe our initial release didn't meet all the requirements for project B, even though project A was doing great. We don't create a new module. We create a feature version for that module. And that feature version provides what project B needs. Project A doesn't have to adopt it. They can continue on version 1, but they can adopt it when they're ready to. You're not forcing adoption on anybody. If there's a bug that needs to be fixed, we create a version for that. When there's a breaking change made by AWS, let's say, I don't know, maybe they're deprecating some of the S3 API values, which is happening next month. We can create a new version that accounts for those deprecated key value pairs. So once that comes out, we start a life cycle. And we go to our teams, we say, hey, here's the changelog for our new module. This is the S3 module. Here's the changelog for it. Here's the reason that's changing. And here are the updates you need to account for in your change. In this case, there's really nothing on the infrastructure side that we need to account for. There's some software changes that may have to be made, but probably not likely. We can put a lifecycle date on the version of the module. So let's say we're on version 2 of the S3 module. Version 3 is the new breaking change. We put a lifecycle of 60 days on version 1 that aligns with AWS deprecation of these features on their S3 API. Now we tell all the project teams, go in there, increment your version. We've already tested the module end-to-end. We've put it in the templates, and we have integration tested it. All you have to do is accept the changes that we've made. We now have 100% code reuse. We are not duplicating code from project to project. We are reusing all of the code we have written 100%. Every module gets reused multiple times. The actual projects simply compose those remote modules into the parameterized infrastructure they need. Project code goes from thousands of lines down to tens of lines. We go from maintaining 3,000 lines of code for 3 projects to maintaining 1,000 lines of code for 3 projects. We've just reduced our maintenance burden for our DevOps team, and therefore the maintenance budget for our DevOps team, by the scale of the number of projects we are maintaining. Every new project only needs net new development. Remember a little penguin from earlier? Now instead of creating a whole new budget for every single project, we reuse 100% of what we've already written, import that through our remote modules, and we write a new module, a new remote module for any missing functionality that we need. So now our projects are truly scalable. And eventually, if you keep doing this and you keep iterating, you'll get to a point where you've covered all the infrastructure you need, and new projects have no new code required. Just simple composition of the already existing remote modules. Templates. I mentioned templates here, right? Templates, so that's what I had shown earlier, was a sample of a template. This is our EC2 template. All you're doing in a template now is just composing the parameterization that's necessary to make the minimum viable environment. You expose advanced configuration abilities, you document those, and you make them available through the module interface. This allows for the standardization of all of your projects on a single code base using the microservice architecture in infrastructure code. This ensures maintainability and scalability of all of your infrastructure projects. Remember this little guy? He's back. Except this time, every time you add a new project, you're going to start with 100% net new code needed, right? Your very first project, you'll have to write 100% of the code. But you get paid back on project number 2 when you only have to write 60% new code. Project number 3, maybe only 30% new code. This is scalable infrastructure code. This is how we start to really save money and start to really save frustration and maintenance time on our projects. Another benefit of this is the predictability that having pre-tested remote modules gives us. We can do all of the necessary testing for security purposes, for code reuse purposes, for the functionality, feature sets. We can do all that testing in the remote modules. Then we come to our templates, where we can test the integrations. We can do all of our integration testing. We can deploy the real environment, test it, and tear it back down in the templates. And we can prove before we even get to a project that 100% of our code works. Now all of our projects can consume a template that's already been tested end to end. No surprises, reduced incidents, and honestly, it's cliche, but time is money, and less time is less money. But, right, there's always a but. This really won't work, right? Because, I mean, number one, sounds too good to be true. Number two, I have a local data center. I don't live in the cloud, right? I have hybrid. And what's the point of tackling half a problem? Well, the good news is this actually works in local data centers too. Your hybrid data center can entirely be maintained this way. You don't only do this for the cloud. Think of what the cloud really is under the hood. It's not some magical thing that lives in the sky. We aren't connecting up to some ephemeral plane pulling down data. It is just another data center. That's all it is. It just has a different interface. We manage it through code because we can. And the only thing you need to do to be able to manage your local data center through code is find the right tool. They're out there. There are tools for everything, from configuration management of your individual servers through Ansible, Chef, Puppet, other tools. Your hypervisors using VMware has APIs, Hyper-V has APIs, Nutanix has APIs. Container orchestration, if you're using Kubernetes or Docker Swarm. Network automation, Ansible has network modules that you can use. Cisco has their own actual built-in infrastructure as code tool. They have APIs built into all Cisco routers and switches that you can use. Storage orchestration, nearly every storage system out there has an API on it. You can use custom providers from Terraform to write custom code for interacting with those if you need to. Bare metal provisioning, Cobbler, Foreman, Metal as a Service, these all allow you to provision physical servers through code. The only thing code can't do for you is take the server out of the box and put it in the rack and plug it in. Once it's plugged in and powered on, code can do everything else for the entire life cycle of that server. So in hybrid, how does that really look, right? So in a hybrid environment, using this methodology, you have one playbook that runs both your local and your cloud data centers. You don't have multiple playbooks because you have multiple tools. You have remote modules that were written for each tool that you then compose together to provide the inputs and outputs that each other need. You can transpose the outputs from your data center locally to provide inputs for your cloud architecture within a single playbook. If you have written these remote modules, these microservices, for inherent interoperability, if you standardize those inputs across all of your modules, then the outputs of any module will be able to satisfy the inputs of another. And now you can really start saving money in the cloud because you don't have to use the cloud for everything. The cloud now becomes your production environment because you want the scalability, you want the edge computing, you want to have the ability to use the power of the cloud to provide your end user production services. But you can develop in your local data center. You don't have to develop in the cloud. Your staging environment may be in the cloud, but now you've reduced the total number of environments that you actually have to deploy to your cloud. So looking back at this, all right, let's recap a little bit here at this point. First, monolith equals bad. Developers learned this a long time ago. We need to learn from their mistakes and accept that developers are right. Monoliths by themselves are bad. Microservice equals good. It's that simple. But why? So number one, we keep maintenance low. When you use microservices, you don't duplicate code. We aren't creating 2,000, 3,000, 4,000 lines of code as we get new projects. We are reusing 100% of all the code we've already written. We can update once and deploy many. When we have proper microservices in our data center for our infrastructure as code, we don't make 12 different changes to update 12 different projects. We make one standard change and we push that version of the module down to our 12 projects. Versioning, very powerful. Once you've decoupled your modules from your environments, you can import modules at a specific version that meets the project's requirements. Not every project needs every feature, and sometimes you may have conflicting feature requirements between two projects, in which case you can maintain two versions of a module. You don't have two code bases. You have version 1 and version 2 of the same code base with slightly different configurations. You also get the benefit of deprecation. Now, instead of having to go out and reach out and touch every single project every time you have to make a change, you can deprecate a version and you'll get warnings in your projects to say, hey, there's a new version out there, new major version. It's a release that you need to adopt. Here's the end of life of the version you're currently on. And here's the adoption path. All of this gets tested inside of your templates for integration testing. So 100% of the testing can be done in a centralized location for the actual remote modules. The only testing that a project team has to do is for their own individual parameterization. But of course, this does not work unless you have that clear foundation that I talked about last week. You need to have clear responsibilities within your organization for who is responsible for maintaining what, where different people sit within the organization, and where they go when they need something. You need a decision framework that empowers your engineers to make the appropriate decisions for their role. They have to have faith that they can do what they're supposed to do. If they're stuck in decision paralysis, everything else is going to fail. And you need a clear style guide to ensure that everybody is developing modules consistently. Inherent interoperability doesn't happen if everybody has their own nuance to how they're going to write the code. And all engineers must be thoroughly onboarded and understand how your organization works within their DevOps. So at this point, maybe I've changed your mind on how you look at your data center. Maybe I haven't. Hopefully you've gained some insight out of this session here. Hopefully you can take this back to your organization and say, what's going on, what we need. Next week, we'll be talking about project management and how we actually roll these things out into an organization and learning from how developers have done similar transformations and managed projects for their tools and their code bases to convert from a monolith into a microservice. That's all I've got for today. Hopefully you had some benefit out of this. Hopefully you enjoyed the presentation. Again, if you have any comments or questions, please send them to the event page, and I will do my best to answer them. Or if you'd like, you can send them to me in a direct message, and I will try to answer them there as well. Thank you very much, everybody, and I'll see you next week.